Howdy everyone. In this video, we are going to learn about what a bill of materials or BOM is and how we can structure or build our own BOM. So this corresponds to learning objective number 3 for this particular lesson. Yeah. So when it comes to a BOM, it is a crucial component which acts as an input for our MRP system. And if you recall the previous video where we discussed the overall layout of the MRP, we saw that the BOM was an input coming into the MRP, and the BOM is typically drafted by those who design the particular part or assembly, and then they hand it over to the MRP system in the form of a BOM. From a definition perspective, the BOM is basically a listing of all subassemblies, intermediates, parts, and raw materials that go into making a parent assembly. And the BOM also has quantities of each of these subassemblies and parts required to make the parent level assembly. And in simple terms, you can think of BOM as a recipe for a product that we are building. And just like a recipe lists the ingredients and the quantities of each ingredient to make that particular dish, a BOM lists the components and the number of components to make that particular product. So this is a direct analogy between a dish and what a BOM is. And next we'll learn about how to draft or create our own BOM. Yeah, now that we understood what a BOM is, now let's look at how it's structured. There are two very common ways to represent a BOM. One is the product tree format, which is on the left, and the second one is the indented BOM format, which is on the right. So let's discuss the product tree format first. And if you look at it, it's relatively straightforward. It's a visual representation that shows how components are assembled into subassemblies and how they build an end product. It's essentially like a family tree for our product, showing how everything is related. So consider the product tree BOM over here on the left. And if you look at this BOM, we are building a BOM for a table. And the table has two subassemblies, the base and the top. The base, in turn, is a subassembly made up of three different components, the legs, the leg bolts, and the frame. Out of these three components over here, the legs and the leg bolts are parts, and the frame is another subassembly, which is in turn made up of four different parts, which are the sides, the ends, the leg supports, and glue. Similarly, the other subassembly required to make the table is the top, and the top is in turn made up of two different parts, the boards and the glue. And all these parts or components that are branched into several other subcomponents or parts are also called as branch nodes, and these represent subassemblies. So in this example, the base, the top, and the frame, these are all subassemblies because they are not individual parts themselves, and to make one of these subassemblies, we need individual parts. For example, if you want to make the base, we need legs, leg bolts, and the frame. So the base itself is not a part. Only when we assemble the legs, leg bolts, and the frame, we get a part called the base. So the base is essentially not an individual part, but it is an individual subassembly. Similarly, over here, the frame is not an individual part, but it's an individual subassembly, which is made up of the sides, ends, leg supports, and glue. And the components over here, which don't branch out, are also called the leaf nodes, and these represent the individual parts. So, for example, over here, the legs, the leg bolts, the sides, the ends, the leg supports, the glue, boards, and glue again. All of these are parts, and these are not subassemblies. And the table, which is the top level component over here, is the main assembly. So if you look at the intended or the structure, the tree level BOM, product tree type BOM, it has a main assembly, which is in turn split into two subassemblies, which are in turn branched down into several individual parts. And let me just quickly rub everything which I've created. Okay. So if you look at these numbers over here, 100, 200, 023, and for legs we have 203. All of them are part numbers representing that particular subassembly or a part. We'll discuss more about these part numbers in the next slide. But now let's focus on whatever quantities or numbers we have in these parentheses. And whatever we have in the parentheses is the number of parts required to build one quantity of whatever is there on top. For example, to manufacture one table, there should ideally be a parenthesis over here. So let's say we have something like this. To manufacture one table, we require one base and one top. These should have been included in the BOM. And now to manufacture one base, we require 4 legs, 4 leg bolts, and one frame, which is basically the numbers in the parentheses. And to manufacture one frame now, we require 2 sides, 2 ends, 4 leg supports, and we require 0.3 ounces of glue. This should also have been included in the BOM. So this is not an example of a perfect BOM. This should have been included. And similarly, when it comes to the table, we require one top to manufacture a table. And to manufacture one top, which is now a subassembly, we require 3 boards. And we require 1 ounce of glue. This should have also been included in the BOM. So in this fashion, we can see that the BOM not only tells what individual parts are required to manufacture a top level assembly, but it also talks about the individual quantities of the parts to manufacture one main assembly. So this was about the product or tree level BOM. Now, the intended type BOM is basically representing this entire structure on the left in the form of a neat table. So for example, the base, which is the first subassembly to build the table, has 3 subassemblies itself, which is the legs, the leg bolts, and the frame. The legs and the leg bolts are parts, and the frame over here is another subassembly, which is in turn made up of sides, ends, leg supports, and glue. Similarly, the other subassembly required to manufacture the table is the top, which is in turn made up of 2 parts, which is the boards and the glue. So all the parts required to manufacture this one table is highlighted in this particular column, and the quantities of each part required to manufacture one table is highlighted in this column. In this way, we can see that once again the intended BOM tells us not only what are all the parts required to produce a top level assembly, but it also talks about the quantities of parts required to produce one top level assembly. And when it comes to the intended BOM, it's also having a structured format where the base is one subassembly, and the components that come within that subassembly have an indentation. They are not on the same level of the base, but they are spaced out, so they have some gap over here. So when we draft a BOM in Excel or Word or any other software to draft a BOM, we will maintain an indentation when it comes to drafting to make sure that there is no confusion between a subassembly and the parts under the subassembly. So we will have an indented neat BOM. So the part numbers over here are the next part, which we are going to be discussing on the next slide. So now let's look at component coding in the BOM, and we can illustrate that through this example where we have 2 BOMs, BOM 1 on the top and BOM 2 here below. From a top level perspective, both these BOMs are exactly the same. They are made up of the same parts, the same components, but the only difference lies in the top. So in BOM 1, the top has a code of 023, and over here the top has a code of 025. And why do these 2 tops have different codes? It's because in BOM number 1, the top is made up of boards and glue, and the boards have a code number of 030, and over here the boards have a code number of 035. So from the individual part in both these BOMs had a different part number, hence the subassembly number was also different, and hence the main assembly number was also different. So each component in a BOM has a unique code, and a product with the same code in 2 different BOMs refers to the same component. And if you look at any BOM, There might be instances in which we have the same name of the component, but the code number is different. And if the code number is different, it means that it is not the same component, but they are different components. And the code number is the basis by which we tell or assess what part it actually is. And let's look at this example over here on the top. So the table has a code number of 100. The base has a code number of 200. The top has a code number of 023. And similarly, the blue is a part which has a code number of 066 and so on. So while the designers or engineers make or design the part, they give part and assembly numbers to each individual component, and that's what is reflected in a VOM. This makes sure that we are talking about the right product in any particular VOM. So let's look at this example. So how many sites which has a code number of 622 are required to build 50 units of model 100 and 80 units. Okay, there should be units. 80 units of model 150. So let's take the first part. We are building 50 units of model 100. So this is 50. So we're building 50 tables. And we've seen that to manufacture one table, we require just one base and one top. It should have been like this in the VOM, but let's just assume that it had parentheses with 1 surrounding it. So to manufacture one table, we require one base and one top. So to manufacture 50 tables, we require 50 bases and 50 tops. Now, when it comes to manufacturing one base, we require 4 legs, 4 leg bolts, and 1 frame. So to manufacture 50 bases, we need 50 into 4, which is 200 legs. We need 50 into 4, which is 200 leg bolts. And we need 50 into 1, which is 50 frames. And finally, to manufacture one frame, we require 2 sides. So to manufacture 50 frames, we require 2 into 50, which is 100 sides. So we require 100 sides, which has a code number of 622 to build 50 units of the table. Now for the second question, how many sides are required to build 80 units of model 150, which is the table model over here, 150. So we again require 80 units of this. So we need 80 bases. Each base requires 4 legs, so we need 320 legs. Similarly, we need 320 leg bolts. And each base requires only 1 frame, so we need 80 frames. And each frame requires 2 sides, so for 80 frames, we need 160 sides. Yes. So now let's look at 2 other inputs into our VOM. The first input is the lead time and the second input is the lot size. So far we have made a VOM. We saw what these 100, 200, 023 mean. So all of them are the code numbers for each subassembly or individual part in the VOM. And we also saw what these numbers in the bracket mean. They represent the individual number or quantities of products required to produce the main assembly. So now let's look at the lead time. So the lead time tells us how many weeks in advance we will have to place an order for that particular component in assembly so that it arrives on time. So for example, for table, which is the main assembly, the lead time is 1 week. And for base, the lead time is 1 week. For top, the lead time is 2 weeks. And similarly, if you go all the way down to the table or the VOM, the sides, which are an individual part, they have a lead time of 1 week as well. The ends have a lead time of 2 weeks and so on. So coming back to the top or the main assembly, the table, the lead time of 1 week does not mean that if you place an order 1 week in advance, you can manufacture and get everything ready. The lead time of 1 week only represents this gap. So for example, considering that you have the base, the top, and everything else ready with you already. So considering that all of these are already ready and you have it with you. It will then take 1 week for the base and the top to be assembled to give a table. So considering that we have this portion of the BOM ready with us, if we place an order right now, we will get a table after 1 week. So the lead time of 1 week over here only indicates how long it takes to manufacture or assemble the table, considering that all the other components below it in the product 3 type BOM are already ready. And lot size is the amount of units that must be produced per order or per batch. So that's also called the batch size. And sometimes companies tend to use that in their BOM. For example, table over here has a lot size of 20. So if you place an order for a table, you can only place it in multiples of 20. You can place an order for 20 tables, 40 tables, and so on. You can never place an order for, let's say, 25 tables or 3 tables, since the lot size is 20. And the lead time and the lot size are inputs for our MRP calculations, which we will be seeing next. So now let's take a look at an example when it comes to a BOM. So what is the shortest planning horizon that should be considered such that there are no shortages of table 100? And to calculate the shortest planning horizon, the method that we use is just writing down individual lead times on either sides of the intended BOM. So for example, this table type BOM has 2 sub-assemblies. So let's calculate the lead times associated with each side. So let's take the right side first. So the lead time for the table is 1 week. The lead time for the the lead time for the top is 2 weeks. We're only considering the right side. Now the lead time for the boards is 2 weeks and the lead time for the glue is also 2 weeks. And the boards and the glue, they don't split further into any individual subcomponents. So the total lead time to manufacture the table from scratch, considering only this side of your BOM, is going to be 1 plus 2 plus 2, which is 5 weeks. But this does not represent the minimum time it requires to manufacture the table, because we have not taken the base, this side of the sub-assembly into equation. So now let's consider that. So let's come to the left-hand side of the BOM. Now to manufacture the table, it takes 1 week. To manufacture the base, it takes 1 week. Now to manufacture the legs, it takes 1 week. To manufacture the leg bolts, it takes 1 week. And to manufacture the frame, it now takes 2 weeks. So to consider the lead time, it's basically the maximum possible time, which represents a worst case scenario to manufacture a product once we give out its notice. So over here, we should consider 2 weeks. Since to manufacture a table, we require everything, the legs, the leg bolts, the frame. And since the frame has the lead time as 2 weeks, it would take 1 week more than each of these components to manufacture the table. So the worst case lead time should be taken into account to calculate how many weeks it will take to manufacture the entire assembly from scratch. And similarly, the frame now splits into 4 parts. Each part has a lead time of here 1 week, 2 week, 2 week, and 2 week. I'm again considering the worst case, which is 2 weeks. And overall, the entire net lead time is 2 plus 2 plus 1 plus 1, which is 6 weeks. So the net, the worst case or the maximum possible time to produce a table, if you give a notice right now, is 6 weeks and not 5 weeks. Because in 5 weeks, we can manufacture this side of the sub-assembly, including assembling it onto the table. But to manufacture this side of the sub-assembly, it takes 6 weeks. So in 6 weeks, that means that we can manufacture this side of the assembly as well as this side of the assembly, because again, it's greater than 5 weeks. It represents a worst case scenario. So if we plan 6 weeks in advance, we can manufacture 20 tables. So let's say 20 tables are required, and we are, today is, let's say it's November 10th. So it takes 6 weeks from November 10th to get 20 tables ready, considering that we are manufacturing or everything else from scratch, or we don't have anything else with us in inventory at all. So the shortest planning horizon, I'll just write it as SPH. For this particular problem, to manufacture one table is 6 weeks. If we only give it 5 weeks, we can probably manufacture this side of the table and assemble it, but we will probably not be able to manufacture the blue side, which is this side of the table. So the next, let me just quickly erase this. Yeah. So now let's consider this problem over here. So in a given week, you determine that there will be a gross requirements for 100 ends, which is code number 411. So we are talking about this particular part. You also know that there is a projected available for that week of 40 units of 411. How many would you order to satisfy this requirement? When would you place the order? So we require 100 ends in one particular week. We already have 40 with us. So now we require 60 more. So we need 60 more, and the lead time for ends is 2 weeks. The lot size is 500. So we have to at least put an order for 500 ends. So now that we need 60 ends, it is well within that 500. And if we require the next 60 ends, if we order it today, we will get it after 2 weeks. So today, let's say it's week 0. In week 2, we will get the 60 ends. So if we want to actually plan for it, and let's say we should have had 100 ends by today, then we should have ordered these 60 ends 2 weeks in advance. So let's say 2 weeks in advance is week -2, because now I'm considering the current week to be week 0. So only if we ordered 2 weeks in advance will we be able to get 60 ends, and combining it with the 40 units that we already have, we will be able to satisfy the requirements for the 100 ends that we need. So this concludes the lecture about bill of materials, and the main inputs again into the BOM, or the main components inside the BOM, are the lead times, the lot sizes, the code numbers associated with each component or a part or subassembly, and finally the quantities of each component required to produce the component right above it. So that concludes BOM, and in our next video we'll be talking about calculations for MRP and how we can automate the entire BOM system. Because if you look at it right now, it looks very clumsy, and we need some structured or easier way to keep track of BOM, to change it, alter it, and so on. And let's say we have a subassembly which has 500 parts. How do we have a structured BOM? That's the next question that we will start addressing in our next video.